So, as we left off yesterday, we were talking about how the structure of the atom is what gives each element its properties. Okay? Now, each element is different. That's part of Dalton's atomic theory. Okay? All the elements, or every element or atom of oxygen is identical, but an atom of oxygen is different from an atom of iron. That's why they have different properties. Why oxygen is a gas and why iron is a metal. Okay? Those properties are based on how many protons are in the nucleus of the atom of that particular element. Okay? So if I have an atom and it has 3 protons in it, it's lithium. And it'll have all the properties of lithium. Okay? If I have an atom that has 8 protons in it, then it's going to be oxygen. And it'll have all the properties of oxygen. Okay? It is the number of protons that determines the properties of the element. Okay? Now, it does say that in here. That is something, okay, that you're going to need to have. Okay? So, how do they differ from each other? Okay? The answer is that elements have different numbers of protons in their nucleus. Okay? And it's these differing numbers that influence the properties of the different elements. Okay? So that's the key thing here. Okay? All elements are different from each other because their atoms are different. Okay? It is, however, just the number of protons that influences the properties, not the number of electrons and not the number of neutrons. Okay? Reason for that is that the number of electrons can change. In a chemical reaction, electrons can be gained or lost by an atom. Okay? So an atom could have more electrons or less electrons than it has protons, and that's not going to change its physical properties. Okay? The number of neutrons can also differ, okay, in things called isotopes. Okay? We don't learn much about that in Science 10, but I could have 2 atoms of carbon that have the same number of protons, but have different numbers of neutrons. They're still going to both be carbon. Okay? They're still going to both have the same physical properties because they have the same number of protons. Okay? Everybody all right with that? Okay. So just remember, because I know I've said this, I think it's about the 7th time I've said this, it's the number of protons, okay, that influences the physical properties of the material. Okay. I'm going to have you guys answer a few questions now based on what we learned yesterday and on this slide here. Okay, just to kind of have some stuff written down in your own words that make sense, because Thursday you will have a quiz on this material, as well as maybe a bit of naming. We'll see how that goes. Okay, but obviously today you didn't have one. I told you that yesterday. All right. So in your science chemistry workbook, okay, so if you go into Google Classroom, okay, in class materials here where it says worksheet booklets, right, you will see your one for chemistry. Okay? If you open that one up, you can just answer the questions directly in that file. It's the same as your notes package. You can modify it, okay, yourself, and then that saves you writing it down on paper and possibly losing it, okay, later, unless you really like to write things down on paper and you're super organized and never lose anything. Okay, totally up to you either way, right? But you can choose on that one. Right, so I've got that one open here, okay, and come on. All right, so the questions are there. Okay, you can put in the answers right in that file as you go along. Right, there's 12 questions there for you to answer. Come. Had it the way I wanted it. Okay, so if you guys can work on those now, okay, probably complete sentence answers. I'll give you about, well, let's say, half hour, 35 minutes or so, right, to work on those questions. Okay, get some good answers. Some of the stuff, like, you're going to look at that and go, oh, that's not in the notes. It sort of is. It's stuff we talked about, and sometimes some of these questions are asking you to synthesize a little bit of stuff yourself. All right. If you have questions while you're working on it, just come up to my desk and let me know. Okay. I'll circulate a little bit as we're working here. But if you need some help, don't hesitate to ask. Oh, speaking of help, I forgot to mention this yesterday. Okay. When my help times are. Okay. So you can come and see me for help Mondays. The entire lunch hour I'm available. Okay. Tuesdays I can't because I have supervision the entire lunch hour, so I'm not in my classroom unless you want to follow me around while I walk the outside parking lots on supervision. Okay. Wednesdays, okay, I can do help in the first half, but I have supervision in the second half. And Thursdays, the entire lunch hour, I'm available as well for help. So if you need to come and see me for some help, that's when you can come and see. All right, how about it there, guys? All right, so question number 1 here. The idea of the atom was first proposed by whom? Who came up with that idea first? Democritus. Okay, so Democritus, the Greek philosopher, came up with the idea of these tiny particles that made up all matter. Okay, his idea was rejected at the time because that idea made no sense at the time. He had no proof. Okay, no evidence that they had supported it. They had this idea that everything was made of 4 elements, and that made perfect sense, and there was lots of evidence to support it, and they could easily teach it to people. So, okay, nobody bought his idea of the atom at the time. Okay, question number 2, what elements did the Greeks believe all matter was made out of? Okay, the 4 of them were earth, air, fire, water. Okay, those were the 4 elements, right? Now, why did that make sense? Because they could see those 4 things in the natural world around them, all right? They knew, like for example, like we used yesterday, steam. Steam was some parts water, some parts fire, and some parts air, because they had to combine water and fire to get it, and then it turned into a gas, which was air. Like these kind of things made sense to them. Okay, they could easily kind of come up with ratios for what everything was made out of. Okay, number 3. During the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. Okay, they were the alchemists, right? And the alchemists' goal was basically to get rich and transmute cheap substances like lead into valuable substances like gold, or make elixirs that could make people live forever. Okay, obviously they were not able to accomplish either one of those goals. Okay, but they did a lot of experimentation in the meantime. Okay, number 4. In the late 1700s, a man used the data from many experiments on matter to develop an idea about the structure of matter. He was Dalton. Okay, John Dalton came up with the atomic theory, okay, and it had 4 points. Okay, the 4 points, all matter is made of tiny indivisible particles called atoms. Okay, point number 2, the atoms of any element are identical, the atoms of different elements are different. Okay. Point number 3, atoms can combine in, this is the most important part, simple whole number ratios to form compounds. And the 4th point is what happens in a chemical reaction. Atoms can be separated, joined, or rearranged, but not changed into other atoms. Okay, in other words, I can't change lead into gold. Okay, that's what the 4th point is essentially saying. All right, looking at this theory, what things do you know of that can prove some of his ideas wrong? Okay, well, the first point does have a bit of a flaw in it. Atoms are divisible, provided you have the technology available to you. Okay, and some atoms break apart on their own. Okay, anything that's radioactive is actually in the process of having its atoms spontaneously break down. Okay, that's why they are radioactive. They are emitting free neutrons in the form of radiation. So we know that that is not necessarily true, okay, all the time. It's true most of the time. Okay, number 6, describe in your own words the models of the atom discussed here. Give a brief explanation as to why each was rejected over the years. Do you think our current model may change? All right, what was Dalton's model? Right, it's just a sphere, right? Solid sphere model, okay? And which was fine at the time. It explained how, you know, atoms could be separated, joined, and rearranged. It was easy to track where things went. It made sense. And then J.J. Thomson came along and discovered electrons. Solid sphere model doesn't explain where those come from or what they are, so he made the plum pudding model that had the solid sphere still being positively charged with small negative charges embedded in it that he called electrons. Okay? Then Rutherford came along and he performed his gold foil experiment, okay? And Rutherford discovered that the atom has actually got a central dense nucleus surrounded by electrons. Okay, so the plum pudding model is out, and now we're into the nuclear model of the atom, okay, Rutherford's model, then Bohr's model, or the planetary model, with the electrons orbiting like planets around the sun, and then finally, okay, to explain how electrons jump up and down in energy levels, okay, we have de Broglie's electron cloud model, which is our currently accepted model of the atom. Okay, question number 7. Okay, as our knowledge increased, we discovered the atom had smaller parts. Name those parts, describe them, and tell where they are located according to what we believe to be true now. Okay, what are the 3 parts of the atom? Electrons, protons, neutrons. Okay, 2 of those are in the nucleus. Which 2? Protons and neutrons are in the nucleus. Okay, electrons are in the cloud surrounding it. That's important because every semester I ask a question like this on your unit exam. I ask you to draw me a picture of a specific atom. Okay, so this is something we haven't covered yet, so it's going to be a little bit new. Okay, I want to draw an atom of, let's say, something simple like beryllium. Okay, so beryllium is right here on my periodic table. Its atomic number is 4. The atomic number tells me how many protons there are in the nucleus. Okay, so if I'm drawing a picture of an atom of beryllium, I'm going to draw a nucleus that's got 4 protons in it. Okay, what else goes in the nucleus? Neutrons. How many are they? How many are they? How many are there? This is a trickier one. Okay, here's how we figure out the number of neutrons, and you might want to write this down because, as I said, I guarantee you this question is going to be on your unit exam. Okay, number of neutrons okay, the number of neutrons equals the atomic mass minus the atomic number. And then round it to the next whole number because obviously you can't have 0.5 neutrons, okay, or even 0.10 neutrons or whatever. Okay, so if we're looking at beryllium, its atomic mass is 9.01 grams per mole. Okay, so if I go 9.01 minus 4, I get 5.01. How many neutrons are in this thing? 5. Yeah, not 5.01. Okay, can't have 0.01 neutrons. All right, so I'm just going to go, okay, and I'll put in my legend, that's neutrons. Okay, so now I've figured out how many particles there are in the nucleus. 4 protons, 5 neutrons. How many electrons are there? Another tricky one. Okay, an atom is electrically neutral. Its charge is 0. So if I've got 4 protons, how many electrons do I have? 4. Okay, there's 4 positively charged particles. There have to be 4 negatively charged particles. Okay, the number of neutrons, or sorry, the number of protons and the number of electrons is always the same in an atom. Okay, once it becomes an ion, then it can be different, but we're not dealing with that yet. Okay, so where do electrons go? Outside, in the cloud. So I'm just going to go like this and go. Four electrons in the cloud. Okay, now I've got an atom of beryllium drawn. 5 marks. Okay, that's a 5-mark question. Okay, here's the 5 marks. First mark, you drew the electron cloud model, de Broglie's model. That's our currently accepted model. 1 mark for that. Okay, 1 mark for the correct number of neutrons, so that's 2. Okay, 1 mark for the correct number of protons, that's 3. 1 mark for the correct number of electrons, that's 4 marks. Having them all in the right place, 5 marks. Okay, because sometimes I have people draw the electron cloud model, put the protons out in the cloud. I don't know why, but that's what they do. Even though it's the electron cloud model, they make it the proton cloud model. Okay, those are 5 marks. Okay, I always ask that question because it tells me whether you understand the structure of the atom and how to figure out how many of the particles there are. It's usually a simple atom, so you're not having to draw 30 protons and 45 neutrons and stuff like that. Okay. All right, back to our questions here. Okay, number 8, 1 cubic centimeter of lead is much heavier than 1 cubic centimeter of carbon. Okay, why would that be? Let's assume that that cubic centimeter has the same number of atoms. Okay, so I have the same number of lead atoms as I have carbon atoms. Why would the lead be so much heavier? Yep, lead has different properties than carbon, and what did we say causes the different properties? The number of protons, exactly. Okay, if we look at the periodic table here, okay, carbon has 6 protons in its nucleus and 6 neutrons in its nucleus. Those are the heavy particles. Okay, if we go to lead, lead has 82 protons in its nucleus. Okay? It's got more protons than carbon has particles. Okay, period. So yeah, lead is going to be way heavier. Its atoms are simply bigger. There's more material in an atom of lead than there is in an atom of carbon, and that's also why they have different properties. Okay, their nuclei are different. All right, number 9, nuclear reactors use atoms with very large nuclei like uranium, okay, which has 237 particles in its nucleus for fission. Okay, fission is the splitting of an atom. Okay, what's the other nuclear process? There's fission and fusion. Okay, fusion is when you force atoms together. Okay, fission is when you split atoms apart. All right, so we use big atoms for fission because they're a bigger target, and they're usually less stable. Okay, third reason, bigger atoms, more energy. Okay, breaking a small atom apart doesn't release very much energy. Breaking a big atom apart releases more energy. There's a lot of energy stored in the nucleus of an atom that holds it together. Okay, and as soon as you break it, that energy is released. Okay, atoms are indivisible. Okay, we kind of already talked about this for question number 10. Okay, atoms are indivisible. Why was this statement believed for so long? Well, because nobody could prove you could do otherwise. Okay, no one proved you could divide an atom or split an atom. Okay, why is it still somewhat true provided no human technology is present? Because very few atoms actually just break apart on their own. Okay, some do, but not very many. Okay, and it wasn't possible to break one up until we developed kind of nuclear physics, and then we figured out how to do it. Right? There's just not something that happens. We don't have knives that are capable of cutting atoms in half. Okay, stuff like that. Okay, number 11. From what you know of the structure of the atom, how do you know the atom, or how does the atom stay intact? Okay, what's in the nucleus? Protons and neutrons. Protons are the most purely positive thing there is. Okay, if you put them next to something neutral, that neutral thing is negative by comparison. It's not actually negatively charged, but by comparison, if you put something incredibly positive next to something neutral, there's still an attractive force between them. They may not be perfectly opposite, but there's an attractive force between them because they're certainly not identical. Okay, and so that creates this force of attraction that holds the nucleus together. Okay, there's different forces. There's like the strong force and the weak force, and all this kind of stuff that's due to subatomic particles like up quarks and down quarks and strange quarks and weird quarks and all kinds of weird different types of quarks. Okay, it's all very like high-end physics stuff, but that's what holds the atom together basically, is this attraction between the particles. Okay, if the neutrons weren't there, the protons would repel each other. Okay, the neutrons provide this buffer that keeps the like things from repelling each other, right? Because opposites attract and like things repel. Okay, so you have to have those neutrons in the nucleus to keep the protons from repelling each other and causing it to break apart. Okay? The bigger an atom gets, the harder it is for those forces to hold the atom together. It just becomes less and less stable. It's like if you just start like putting blocks in a in a tower. Eventually the tower becomes unstable just because of all the extra mass that's involved. Okay? It's the same with an atom. You keep trying to put more and more mass in an atom, it just becomes less and less stable. Okay, same principle that makes glow-in-the-dark materials work is used by plants to produce food. We talked about this yesterday. Okay, this has to do with the electrons jumping from one level to another. Okay, so when light is applied, okay, to a plant, to the chlorophyll molecule, the electrons become excited, they gain energy, and they hop from one level to a higher energy level. And then when the light is gone, they fall back down and they release the energy they gained from the sun, and that energy is then used to break up carbon and water and make sugar. Everybody all right with that? Okay. Questions on any of those? All right. Make sure you keep those answers for you to study from before you finish these. All right. I'm going to give you guys about a 5-minute break here, and then we are going to get into naming compounds. Okay, after that. So if you can find lesson 2 in your notes packet, that's what we're going to be doing in 5 minutes time.